These are the azimuth and elevation modules of my SatNOGS Antenna Rotator. Before I finalize the assembly and build an enclosure, I want to find out whether they actually work. To understand how we got here, we need to go back to the beginning. This project started with a FreeCAD model. From there, I exported every part as step files onto my GitHub repo. The link for the model and the step files are in the description. I briefly considered converting an entire rotator to imperial hardware, but metric tubing and fasteners are easy to source nowadays, so I kept the design in metric. With the exception of the axle stickouts, the azimuth and elevation modules are identical. Originally I planned to print everything in nylon, but Gulf Coast humidity made me reconsider. I rediscovered a forgotten roll of ABS and decided to use it instead. ABS has become my favorite filament, though some parts needed some extra brims to help with bad adhesion. A previous video shows how I printed and prepared the worm screw with its steep, severe overhangs. Assembly of the worm screw assemblies is straightforward, although I spent far too long chasing the perfect 44mm reference distance. Later on, I will throw it away and readjust the axle stickout so both assemblies fit cleanly into their bearing blocks. For now, I'm using my small arbor press to seat the bearings. The shaft collar locates one of the axle bearings. It's keyed to the axle using grub screws and embedded M3 nuts. Later, we're going to drill holes into the axle for the screws to bite into. The nut pockets are tight, so I use M3 bolts to pull the nuts into place. The other end, the encoder gear locates the bearings and houses the homing pin. Again, grub screws and M3 nuts secure it to the axle. And again, I use bolts to pull the nuts into their pockets. No drill holes are required on this end of the axle as there is no torque transmitted. The bearing assembly consists of the bearing, its housing and the retaining plate. The arbor press easily seats the bearing, and the plate prevents it from sliding out. Up to this point, everything is going smoothly. This is where the project goes sideways. The inner hole diameter of the 3D printed parts was a few tenths of a millimeter too tight. I tried pressing and hammering them on. That didn't work. I sanded the holes even though I knew better. With enough force, I got the gears and collars onto the axle, but they were so tight that tuning and adjustment inside the frame would be impossible. But that's a future problem. Let's ignore it for the moment. The outer axle diameter was also a few hundredths of a millimeter too wide. I tried persuasion, heat, cold, but nothing worked. The bearing simply wouldn't go on. At this point I knew the video would need to be delayed. If I'm going to continue this project, I might as well do it right. I mounted the axles in my lathe and worked down the outer diameter with sandpaper, starting at 80 grit and finishing at 320. The stickout was excessive. Yes, the setup is sketchy, but the sandpaper strip let me both sand and stabilize the axle, and WD-40 helped lubricate the abrasive. Eventually I smartened up. I broke off all the 3D printed parts already mounted and moved the axle to my combination lathe, which has just enough bed length to support the axle tube with a live center. This let me sand and polish the entire axle to proper bearing size. To locate the grub screw holes, I used the shaft collar itself as a drilling jig. A spacer cut from Schedule 40 pipe positions the collar correctly. I clamped the collar to the axle with 3 crop screws and used the last hole to index the 2mm drill bit. Again, WD-40 is used to lubricate the drill. Since I broke off all the 3D printed parts from the axle, I printed them again. This time I bored the holes out on the mini lathe for a perfect slip fit on the newly polished axles. Reassembling the axle modules was now trivial. The shaft collar and collar gears and bearings all slide on cleanly. And the bearing blocks can clamp them precisely within the frame. Next, the frame. I use my chop saw with a carbide blade to cut the 14 cm and 10 cm segments from 1 meter 2020 profiles. A stop block ensured consistent 14 mm cuts. Two 2020 cutoffs acted as spacers for the 10 cm cuts. The 14 cm segments turned out 1.5 mm too long. When test fitting the assemblies, I realized I did not have enough margin to tension the belts. So I glued up a small jig to safely shave off the extra 1.5 mm. Without the jig, clamping the short segments is nearly impossible and the cuts would be unsupported. Only afterwards did I remember that I wanted to wax the blade or lubricate it with WD-40. Luckily, the cuts were clean and straight. No harm done. Frame assembly is mostly a matter of slowly tightening the bolts of the interior L brackets and letting the bolt action pull the joints together. The trick is to keep it loose and slowly tightening all up. Order does matter though. Assemblies like the stepper motor block access to screws. And sometimes I have to remove a frame segments to reach a hidden bolt. Eventually, I learned the correct sequence. Piece by piece, the azimuth and elevation module came together. With the mechanical build complete, I set the power supply to 13 volts, connected the stepper motors to the controller and plugged the controller into my laptop. I commanded a 360-degree rotation. The axle didn't stop after one turn, it kept going. Some testing showed that both axles rotated 8 times more than commanded. Checking the source code revealed the issue. The firmware expects a microstep resolution of 1/8 step, but I had left all microstep jumpers open, which yields full steps. I soldered in the 2 missing jumper bridges. Now it works exactly as expected. The axles turn to the commanded positions. I am having so much fun just rotating axles around. So what's next? The remaining tasks are connecting the 2 modules, closing off the sides, putting the controller into an enclosure, permanent wiring, building a stand or tripod, and of course, building and adding an antenna. We'll tackle all those in future videos. Thanks for joining me at 4111 Spyglass. See you next week.